Ask a chatbot about your own company and watch it make things up. Ask about last week's meeting notes, your internal wiki, the pricing doc you wrote yesterday, and a confident, fluent, completely wrong answer comes back. It's not broken. It has literally never seen your data. So here's the question this whole video answers. How do you make an AI answer from your documents, the private ones, the fresh ones, the ones it was never trained on? The trick behind every chat with your docs feature, every support bot that actually knows your product, every AI that cites its sources is one pattern. It's simpler than you think. It's built directly on embeddings, and by the end of this you'll be able to draw the whole thing on a napkin. Let's build it. Here's why the model lies. A language model is trained once on a giant snapshot of public text up to some cutoff date. All of that knowledge gets baked into frozen weights. It never saw your internal docs, your customer records, or anything that happened after training finished. So when you ask about them, it does the only thing it can. It predicts the most plausible sounding words. Sometimes that's right. Often it's a beautifully worded hallucination. The right shape, the right tone, a made-up refund window, and an invented policy number delivered with total confidence. And you can't just paste everything in either. The obvious fix is to dump your entire knowledge base into the prompt, but you can't. Even a large model's context window fits maybe a few hundred pages at once. Your company knowledge base might be millions of pages, growing every day. You physically cannot stuff it all into the prompt, and even if you tried, it would be slow and wildly expensive. So we're stuck. The model has no idea about your data, and there's far too much of it to simply hand over. That is the problem we're about to solve. So here's the fix, and it's almost embarrassingly simple. Don't retrain the model. Don't cram everything into the prompt. Instead, look it up first. When a question comes in, go find the handful of passages from your documents that are actually relevant, and hand only those to the model as context. Then let it answer using what you just gave it. Retrieve, then generate. This pattern has a name, 3 letters you'll see on screen a lot. Officially, it's called Retrieval-Augmented Generation. But honestly, forget the jargon. The whole idea fits in 4 words. Look it up first. The model stops guessing from memory and starts answering from a source that you control. That single move is the difference between a chatbot that bluffs and an assistant that actually knows your stuff. Think of it like the difference between a closed book and an open book exam. A raw language model is a brilliant student taking a closed book test. It has read almost the entire internet, so it's shockingly good, but for anything it didn't memorize, it has to guess. Retrieval turns it into an open book exam. Same brilliant student, but now, before answering each question, they get to flip to exactly the right pages of your textbook and read them first. The intelligence didn't change. What changed is that the answer is now grounded in the material sitting in front of them. Or picture a sharp new hire with a great research librarian. They don't know your company yet, but ask a question, and the librarian instantly slides the 3 most relevant documents across the desk. That librarian is the whole trick we're building. It starts with your own documents, all of them. PDFs, help articles, wiki pages, chat threads, code, transcripts. But you don't store a document as one giant blob because a single file might cover 10 different topics, and you only want the paragraph that answers the question. So first you chunk. You split every document into small, focused passages, usually a few hundred words each, often with a little overlap so you don't slice a sentence in half. One long onboarding guide becomes 50 tidy chunks, each about one thing. Why bother? Because retrieval is only as good as the pieces it can grab. If your chunks are huge, you drag in piles of irrelevant text. If they're too tiny, they lose their context. Get the chunk size right, and each piece becomes a clean, self-contained little answer, just waiting to be found. Chunking is unglamorous, and it quietly makes or breaks the whole system. Next, every chunk gets turned into numbers. This is where embeddings come in, and if you saw the previous video, you already know the move. You send each chunk to an embedding model. OpenAI has a popular one, and it hands back a vector, a long list of numbers that captures the meaning of that text. Similar meaning, similar numbers. How do I reset my password and I forgot my login land right next to each other, even though they don't share a single keyword? You do this once up front for every chunk in your knowledge base, thousands, even millions of them. Each one becomes a point in meaning space. And here's the key detail. You'll embed the user's question later with the exact same model, so the question and the answers live in the same space and can be compared directly. Text goes in, meaning numbers come out. Those vectors need a home, and it's a special one. You don't just dump them in a normal database, you put them in a vector database. Its entire job is to store millions of these vectors and, given a new one, find the nearest neighbors almost instantly. Ask a regular database for rows where the meaning is similar, and it has no idea what you mean. A vector database is built for exactly that, nearest neighbor search over meaning at scale in milliseconds. This is a whole topic on its own. Think Pinecone or Postgres with the pgvector extension or Chroma. What makes them special is the index, a clever data structure that lets them skip almost every vector and still find the closest matches, instead of brute force comparing against all million of them. For now, just hold one picture in your head. A giant cloud of points, one per chunk, indexed so that find me the closest ones is lightning fast. Your documents are now a searchable map of meaning. Now the interesting part, the retrieval step itself. A user asks a question. First, you embed that question with the same model, turning it into a vector in the same space as all your chunks. Then you ask the vector database one thing: which stored chunks sit closest to this question. It measures similarity, ranks everything, and you keep just the top few, usually the top 5 or so most relevant passages. Sit with that number for a second. Your knowledge base might hold 1,000,000 chunks. Retrieval throws away all but 5. That's the magic. Instead of drowning the model in everything, you hand it the 5 paragraphs that actually matter. It's like a search engine, except it ranks by meaning instead of matching keywords, so it finds the right passage even when the words are completely different. 5 chunks, that's usually all it takes. Here's the sleight of hand that ties it all together. You now have two things: the user's original question and the top few chunks you just retrieved. So you build a brand new prompt that stitches them together. It looks roughly like this. Here is some context. Then you paste in the retrieved passages using only this context, answer the following question, and then the user's actual question. That assembled prompt is what the model actually receives. The user typed one sentence. The model sees that sentence wrapped in exactly the right evidence, pulled fresh from your documents. This is the augmented part. You've augmented the prompt with retrieved knowledge. And notice you can slip instructions in here too. If the context doesn't contain the answer, say you don't know. That one line is how you stop the model from bluffing when your documents come up empty. Only now does the model answer, and this is the payoff. It takes your augmented prompt and generates a reply, but grounded in the passages you handed it, not in fuzzy training time memory. The same model that was hallucinating a minute ago is now reading straight off the page you gave it. Because the source text is sitting right there in the prompt, the model can quote it, summarize it, and, crucially, cite it. Good systems return the answer plus links back to the exact chunks it used, so a human can click through and verify every claim. That is a genuine superpower. The answer is fresh because you can update your documents anytime. It's private because your data never had to be baked into the model. And it's checkable because every claim points back at a real source. Same model, same weights, but now it's answering from your world instead of guessing about it. Let's watch the whole thing run start to finish. Ahead of time, offline, you take your documents, chunk them into passages, embed each passage into a vector, and store all of it in a vector database. That's the setup, done once and refreshed whenever your docs change. Then at question time, live, a user asks something. You embed their question, search the database for the closest chunks, grab the top few, paste them into a prompt alongside the question, and send that to the model. It answers with citations. Documents chunk, embed, store, then retrieve, augment, generate. That's the entire pattern. 7 steps, 2 phases. Everything else you'll ever read about this, re-ranking, hybrid search, fancier chunking, is just polish on top of these 7 boxes. Learn to draw this, and you understand almost every AI that knows your data product out there. You've already used this without knowing it. When Perplexity answers a question and shows little numbered citations under each sentence, that's retrieval live over the web. When a company's support chatbot actually knows their return policy and points you at the right help article, that's retrieval over their support docs. Chat with this PDF tools. Retrieval over one file. An AI coding assistant that answers questions about your specific repo. Retrieval over your codebase. Internal company search, the thing that finally lets someone ask what's our parental leave policy in plain English and get the real answer with a link. That's retrieval again. The pattern is everywhere because it solves one universal problem. General intelligence, meet your specific, private, constantly changing data. Anytime you see an AI that cites its sources and knows things it could not possibly have memorized, you are looking at this. You don't build this from raw parts every time. There are frameworks that hand you the whole pipeline as ready-made building blocks. Loaders to read your documents, splitters to chunk them, connectors to the embedding models and the vector stores, and the retrieval logic already wired together. LangChain is the best known one. Llama Index is another, built specifically around this look it up then answer flow. This is their actual documentation, and notice the whole library is basically organized around the very steps we just drew. Load, split, embed, store, retrieve. You could wire it all up by hand with a few API calls, plenty of people do, but these frameworks exist because everyone kept rebuilding the same 7 boxes. Start from one of them and a working prototype is an afternoon, not a month. Now for the part that bites people in production. First, retrieval is everything. If the right chunk isn't retrieved, the model literally cannot answer correctly, garbage in, garbage out. Most of the AI's dumb complaints are actually bad retrieval, not a bad model. Second, your index goes stale. The model answers from whatever you embedded, so when a document changes, you have to re-embed it, or your bot will confidently quote last quarter's pricing. Third, chunking is a real decision, not a default. Split too coarse and you bury the answer, too fine and you lose the context around it. And fourth, this does not teach the model anything. The weights never change, you're handing it notes at question time, not giving it a permanent memory. So get retrieval right, keep your index fresh, and always show your citations so a human can catch the misses. So let's pull it together in 3 lines. 1. A model only knows its training data, so for your private, fresh documents, you look it up first instead of asking it to remember. 2. You chunk your documents, embed them into meaning vectors, and store them in a vector database so you can find the most relevant pieces by meaning. 3. At question time, you retrieve the top few chunks, paste them into the prompt, and let the model answer from that real context, grounded, fresh, and cited. Retrieve, then generate. That's the whole thing. If this finally made the whole retrieval thing click, do the one small thing that helps this channel most: subscribe so the next one finds you. And it's a perfect follow-up. We've leaned on the vector database this entire video without ever opening it up. Next in the series, we go inside, how a vector database actually finds the nearest neighbors among millions of points in milliseconds without checking them one by one. That's where retrieval gets its speed, and it's genuinely clever. See you in the next one.